So leading ones as opposed to free variables. So free variables are the ones that do not correspond to leading ones. Okay, so as you can see, those the blue ones are correspond to free variables. Remember, every row in the matrix corresponds to an equation. Every column corresponds to a variable, right? By design. So then whichever if we are able to create leading ones, those are the variables that are well, not free in a sense, not free. They're, well, you can call them dependent if you like. There might be other terms, dependent variables, and these are free or independent variables. Why so? Why the name is seen is here once you solve the problem. Remember, this we had two examples at the end of last class, and this is the first one. So as you can see, we solved the system. Okay, solution of row operations doesn't matter how it exactly happened. The end result is what we're paying attention to. As you can see, what has happened is well, this over here is clearer. Clearer. What has happened is the leading or dependent variables. The ones with leading ones are x1, x2, and x3, right? So see that diagonal over here of elements. They are all have no coefficient, meaning that coefficients are ones. Okay, so these are leading ones. Okay, so these are the leading ones, and these are variables end up to be dependent on what? On the x4. x4, which is the independent or free variable. Okay, so once again, these are dependent. And this is the only one is free. So far, certainly you can challenge that y x4 and not another one. But the way we worked it out is at the end, bottom right, as you can see, everything, or rather left, bottom left, everything is expressed in terms of x4. And then to make that, drive that point all the way through and have a vector representation, and for that purpose. An important one. That's why x4 is we rename x4 and we call it t. Okay, so that is that's how free we about that variable we can rename it. And then as you can see, then we express x4 in terms of everybody, including x4 is expressed in terms of t. That's this equation. And finally, we have an equation for the in vectors. Okay, so as you can see in vectors, in the so it's you cannot really, yeah. I guess you can tell which it is now even hard to recognize which of the variables are free and which ones are dependent at the end. But it doesn't matter. The solution is perfect. It represents a straight line. Okay, so. And we're going to analyze that in a minute. But the second example, once again, we skipped over all the row operations, and suppose we already have carried out some of these operations somehow, right? From somehow we arrived to this augmented matrix, okay? And then we went back to augmented matrix. It is not technically a matrix, remember? So we are not doing any kind of matrix algebra while we're getting there. So it is no loss of kind of a algebraic approach. Remains invisible while we do one more step and convert back into equations. Okay, so that's what happened here. Back into equation, even though we already, let's mark these. So once again, these are dependent. These two, x1, x2 are dependent. And these are free or dependent or independent. Okay, so once again, leading ones. Leading ones are the ones that determine whether or not a variable is one or the other kind. Okay, but then that's okay. It just points out how we're going to proceed from it, and why we even have to proceed. Even though it seems like over here the problem is solved, but really if we pursue a vector representation of the answer, it has to represent all x1 to x3, x4. So vector consists of the four numbers, and that's when we have to then we have to have four equations. For variables, you have to have 4 equations in each of those, not for variables, meaning 4 components of the vectors you're trying to find, and that's why you cannot have 2 equations, you have to have 4 equations. So that's the crucial step here. This one, we need 4 equations. Just as in the previous example, the exact same happened here. As you can see, we needed 3. Because the space, the number of variables 3, the space is 3-dimensional, you need 3 equations to directly, explicitly express these vectors in terms of parameters. Question?
In set 07, we had 5 problems, right? But now there are 6 problems.
The current homework?
No, not the previous one.
From last week?
Doing it, there was only 5 exercises. And now if I see it, it's like 1 additional.
It may have.
6 in total.
Yeah, I may have made a mistake at some point. I started to add problems before I created a new homework, and there might be some of them ended up in the old homework. Okay, so I'll check it out and make sure that there's no problem there. So the last problem, if it is, so you didn't get to do it, obviously, because I added after it was due, so I'll take care of it. Okay, so as you can see, it is in fact 4 equations by the number of variables. Some of them are trivial, so these 2. So the equations for the free variables are trivial in that sense. They're simply, it's like a renaming. So that's renaming for the most part. But then once you turn these 4 equations into vector equations, 1 vector equation, then that part becomes unimportant. So it's just 2 parameters. 2, so this is where we ended up last time, and so we need to complete what is that we are looking at. What I said, it is a plane, and indeed if you look at the variables, at the what varies and what does not, x varies. Okay, so let's rename these 4 vectors. It is vector x, as always we have done. So x belongs to R4. Okay, then all of these vectors belong to R4. Then let's call this vector S plus T. How about V plus SU? Okay, so 4 vectors, those capitalized letters X, S, T, S, X, S, V, U are the 4 vectors in fixed vectors in the no, only S, V, and U are fixed, and X is variable. So what does it make it? What makes it variable is are these, the 2 parameters. The parameters, that's why we can vary X even though S, V, and U are fixed. Parameters, so they're variable. This is also variable. But these 3 are fixed. So we found them from the description of our system of equations. Okay, so now let's try to visualize what we have, considering the fact that the space is 4-dimensional, so it might be a challenge. But since it is solved, the problem is solved. It's possible. So let's start from right to left. So let me try to have these 4 vectors visible. Let's start with 2. The S and U and B. Okay, so say this is U. Okay, okay, and then suppose this is the origin. This is gonna be S. Okay, so if you look at it, then just at the beginning, suppose what this picture describes is a particular X. This is X. Or at least one possible value of X is right here. This could be X. It is X for one of a particular choice of our 2 parameters. It is X with what? T equal 0 and S equal 1. Okay, so these are 2 parameters that they are not only they're variable, they are absolutely unrestricted. That's what free variables or independent variable means, you remember, independent variable in a function, that's what exactly it means. There is no restriction on it. Certainly not in the linear situation, so there is no issue of the domain. So also independent variables, they can vary any way you like. So in this particular case, I choose choose t equals 0, s equal 1. Then what is the meaning of my vector x? One of the solutions. So this is one of the solutions. And that's you can see it here. Okay, so it simply will be s plus u. Okay, and then so let's keep t equal to 0, and then we vary this s lowercase. What's going to happen? We're going to get more and more u's. So if I'm looking at this is twice 2u, 3u, and so on. So as you can see, it is a straight line. Negative u, like this. Okay, so if I allow v to vary, I'll have what I'm going to end up with is a whole straight line. Okay, so now, well, you can guess what's going to happen next. What's going to happen next?
You have a value, you have t being non-zero value.
Right. So we're doing the same thing with t. So I'm gonna set. Well, first of all, let me plot vector v here. Say v. Okay. So the whole thing is a four-dimensional space. So well, consider that. And then, as you can see, then I want to plot a solution x with t equal 1 and s equals 0. Okay, so that's going to be, this is the one. Oops. This is x with t equals 0, no, t equal 1, s equal 0. Okay? So u is out because s equal to 0, so I'm dealing with vector v only. So I add to sv, and then I'm getting, this is 2v, 3v, and so on, and then negative v. I end up once again with the whole line. So the orange line is where what t is equal to 0, and the green line is where s is equal to 0. The other variable, the other parameter it varies arbitrarily. So one parameter is allowed to vary, the other one is fixed at 0, the other one allowed to vary, so the result is a straight line. So we have two straight lines, but we only have two straight lines when we allow only one variable to vary, but if we actually allowed and require to vary both, which means what? It means that these two lines will determine a plane, right? So all of the intermediate variables are also possible. So if I try to visualize this, maybe like this. So some more, like this. Okay, it might look like this. Okay, so that's how I'm trying to visualize the plane here. So the origin, as well as everything else, is below it, and it looks like a kite. Right, so two frames, one, the green straight line, the orange straight line creates the other frame, and then you stretch a piece of fabric on it, and you have a plane. And that is the plane that we are found. Okay? So the idea is just a one step up from the last example where the answer was one straight line. So let me quickly visualize this. So this is, once again, I could call this x. I call this u. Actually, we need four equations. It's two equations over here. So x, I call this s again, and I call this v. Okay, so the equation is x equal s plus t v. Okay, and then the plot is, we already know what to do, so we can just so this is 0, this is s, and from the end of s I'm adding multiples of v, like this v, and then this is the solution set. The solution set is all the vectors with the endpoint on the straight line. Okay, so all of these are solutions. So in this case, it's still everything is happening in four-dimensional space, but the end result is a straight line. It's a one-dimensional space. Okay, so when you have two parameters, you end up with a picture which is bigger. So you have a plane, and that plane is once again the solution set. Okay, so once again you have a point underneath. You have a plane and resting on the tip of vector S, and the direction of that plane is determined by those two vectors V and U that we found. Okay, so that is the geometry behind the solution. This is a four-dimensional space, so there are more possibilities that we have not explored. So just two, as you can see, line and plane. So let's explore it quickly. So this is like a example one. So a line, a plane. There are two more. What are they? Well, there are actually three more. So if we go down in size, where we're going to end up? From a line, we go down in size. What would that be? What? A point, right. A point. So a point is still a possibility. So once again, remember how I did it last time? I took this equation, which gave me a line, and then I made up the last example. So if we look at this example, and how do we create a point? Well, we saw already examples of when the answer is a point. It is when there are no free variables. There are no free variables, and every variable means it's dependent, and it is equal to an exact value. So the equation would be, so another example, the equation would be x equal s, whatever that s is, right? So think about, well, maybe I'm jumping forward too fast, but it would be looking like this. x1 is equal to, say, 1, x2 is equal to 3, x3 is equal 3, x3 is equal to 0, and x4 is equal to 5. Okay, so that you went through all the, once again, remember, this is a row echelon form, which happens to have the simplest kind, like this, with most trivial situation, and you have 1, 3, 0, 5. So once again, we somehow arrived, through elementary row operation, we arrived at that augmented matrix on the right. Then we discarded the matrix structure, augmented matrix structure. We ended up with three equations, right? Each variable is determined, and then if we want to write it up now in the vector format, then what does it look like? We already know it's going to be x1, x2, x3, x4 equal to a vector 1, 3, 0, 5. Naturally, this is x, this is s, and so our matrix equation that looks complicated in different circumstances is simply x equal s. So there are no parameters. No four leading ones, which means that there are no free variables, which means that there are no parameters. Okay, so that is the one possibility. Remember, there's even a smaller possibility. I'm not going to look into that just now, but no solutions is always a possibility. So once again, you can think of something happens, and there is there are fewer than four leading ones, and yet. Well, we had that example like that, so let's just not spend time on that. But there are more possibilities. That four-dimensional space, so there will be more possibilities as many as free variables you've got. Okay, so we have examples for the case of no free variables, one free variable, and two free variables. Okay, you can still how many can you have? You can still have three, and you can have four. Okay, so like I said, as you can see, the examples are made up in their reduced row echelon form, and you can, whatever numbers you pick are available. They are possible. So all of these cases are possibilities. So I could make up possibilities when I will have 3 variables. I could make up possibilities that I have 4 variables. It's entirely up to me. Just choosing the appropriate leading combination of leading ones, or the appropriate form of the reduced row echelon form of the augmented matrix. So let me try to summarize. Based on this, since we're doing dimension 4, let's just as well do dimension 4. So reduced row echelon form. Reduced row echelon form. Okay. So like so 1, 1, 1. Okay, like this. And how about this? So as you can see, these are all zeros. Above, it doesn't matter what it is. So solutions. So this is reduced row echelon form on the left, and on the right, I'll have the solution set. So what's the solution set here? Look at the last row. The last row is made of zeros except for the last entry.
Oh, so it's not.
Yeah. What? There's no solution. Right.
It's not row echelon.
No, it is the row echelon form, but there is no there are no leading ones or anything else left in the last row. Okay, so and I end up with 0 equal to 1, no solution. Okay. So you're familiar with this symbol?
Yeah.
The empty set. The empty set, and when we want to say that there's no solution, so that's what we use. Now, if I take this thing and I add a leading 1, and it doesn't matter really what happens elsewhere, like that, hold on, like 1, 1, 1, I need another 1, like this. Okay. Okay, so same thing, except I have a leading 1 now at the bottom.
So in the first one, that last one is just part of the solution?
No, this is the vertical line. Remember, that separates
okay.
it. Yeah, so in the right-hand side, there is a value that is not 0.
Yeah, okay.
Okay, so we added a leading 1. The answer is 1 solution, right? There is 1 solution. So let's call it S. Where this S is, this is where S is, that vector. Okay. So and then what else can happen? We could have now the reduced row echelon form will have fewer and fewer leading ones. So how about we have 3? So we already saw it, but let's just as well do it like this. So I have 3 leading ones. So these are still zeros. The last row doesn't look right. Just 1 row here. Okay. So okay. So there are 3 leading ones, and there is 1 free variable. That was the example, the first example from last time. Okay, so this is the one free variable x4. Okay, so well, let's call it, we call it t as a matter of fact, right? So then the answer was, so x equal to s here, x equal to s plus t tv. So s is the same. Once again, it is the last column. And now this is v. This is vector v is here. Well, okay. Let's try to squeeze it here. So that's where the vector v is. Okay, so let me confirm that this is indeed the case. So this example I'm talking about. And where is my vector v? This is my vector v. See over here, where did it come from? It came from, it is -2, -1. It is indeed right here. This is my vector v with an extra 0. Naturally, sometimes you drop the row that has only zeros in it, but as you can see, that kind of you lose some of the it just gets a bit more complicated than necessary. You still need 4 equations. So that's why I do it in such a way that the kind of uniform, so that no matter what, you always have 4 rows in your augmented matrix. Okay, so as you can see, I have 4. Vector v is the last row that corresponds to the single free variable. Okay, now I do the same. I have the same thing, but now I have 2 leading ones, only 2, like this. Okay, like this. So these are still zeros. I have still my vector s here, and here I have 2 vectors like this. Okay, say this is v and this is u. So 2 columns in my augmented matrix. Let me plot the leading ones again. So 1, 1, 1, 1, 1, 1, 1, 3 ones, and only 2. So as that was the last example, x is equal to still s, the last row, plus s lowercase u plus tv. Okay, so you can see how the degrees of freedom, degree of freedom increases, and you have more and more solutions in the sense that in that sense that there are more degrees of freedom. At the same time, and you know that geometrically the size, the dimension is what is increasing, the dimension of the solution set. So dimension, not the dimension of the space. Dimension of the space is 4. So 4 variables, the space of 4 variables is are 4. Okay, but now the dimension of the solution set. Dimension 0, 1 point, dimension 0, line, dimension 1, plane, dimension 2. Okay, empty set has no dimension, but some say it should be -1. But just, yes, you can see it fits. If you want to come up with an idea of what is the dimension of the empty set, you have to say that it should be -1. But it's unnecessary. But as you can see, that is how things work out as we were proceeded to 3, and a 4 is also a possibility. So 3 and 4, depending on how many. So once again, how many leading ones we've got. So you can see the solution will be x is equal to s plus, say, what is the variables I'm running out of, r w plus su plus tv. Okay, so that will be the space of solution is 3-dimensional. Okay, that 3-dimensional space located in our 4-dimensional space of unknowns. Okay, so the restrictions, as you can see, there are fewer and fewer restrictions. Reduced row echelon form gives us a net result. So the matrix originally might be very complicated, but if we reduce it to this, then we know how many degrees of freedom we are left. Is it even if we do not determine specifically what the answer is, we can figure out at least what the dimension is, and ideally what this representation in the middle is exactly what we want to have. Okay, so this here we have a 1 leading 1 and the last one. So this is a bunch of zeros and 1 leading 1. Well, I forgot to make sure that these we have a match here, like this. So if there is no match of zeros on the left to zeros on the right, we have a conflict and there is no solution. And so we were in the very first case. So the last case is very simple. So it is possible that you start with equations, and what is the worst case, not worst case or best case scenario, depending on what it is. What's the augmented matrix here? What does it mean that the solution set is 4-dimensional? In the 4-dimensional space.
It's everything.
It's everything. Okay, so what kind of a system of equations gives you everything? Who?
X 0 equals 0.
What?
X
A 0 equal to 0, so that's like this. Okay, so no leading ones. No restrictions whatsoever on any variables. Okay, so that's like I want to put an arrow here to emphasize once again that we're talking about elementary row operations that from some matrix that you start with, that's where you end up, and then you are able to write up the equation. So x, there is no need to write any restrictions because x is everything. So then we match different shapes of reduced row echelon forms on left with the algebraic representations of the solutions in terms of matrix algebra, specified parameters. So I'm not sure how clear I made it, but the these little letters are the free parameters, so you can plug in any value that you want. That's what creates the whole space of solutions rather than a point. The t varies, and it's not a point anymore because t is absolutely arbitrary. You add any multiple of v is being added to s, and that's what creates a straight line. And then you just, in the next two cases, you have, or rather than having one line, you have 2 or 3 lines, and combined together, they are allowed to be combined. You end up with a 2-dimensional space, a plane, or you end up with a whole 3-dimensional space, just like ours. Okay, so R, R2, R3, and this is R4, the whole thing, point. Okay, so so these are, I say R2. We're speaking of copies of these spaces. So we certainly know what, say, R2 is. That's XY plane. That's pairs of numbers. That is not exactly what we're observing over there as it is represented here. So I prefer to speak, at least for the time being, of copies of these spaces. So, for example, in this case, that's the most interesting, I suppose, kind of in the middle of the road. The solution set is a plane, geometrically speaking, but algebraically you can say that it is a copy of R2. So we know what R2 is. What copy we still haven't clarified yet, but it'll do for now. So if we know what it is, a plane, imagine that plane placed inside of the 4-dimensional space, and that's what the solution looks like. So let's try to summarize this in a more general case of n-dimensional case. So I can't call it a theorem, so I'll call it just an idea. So how should I put it? So so a system AX is equal to B in Rn may have as its solution set one of the following. May have, well, must have. One of the following. And the list, we already had a list for 4-dimensional space from -1 to 0, so it's pretty much the same, only the list is longer. So starting with the empty set is R, R2, R3, Rn. Okay, so one of these. So it is not, a solution set could be anything. Just to contrast with the nonlinear situation, you take x squared is equal to 1, an equation of one variable x, this is not capitalized, just real numbers, and the solution set is x is equal to plus or minus 1. So in other words, it is, we have, the solution set is 2 numbers, right? So it is very different from what we see here. So because the solution set is in fact a copy of a Euclidean space. So you cannot have 2 points. If you have 2 points, then everything in between will also be a solution, and everything beyond like this. So if you have 2 points as solutions in the linear situation, then suppose you have 2, then you have to add these as well. Okay? If you have 3, they might form a plane and so on. So that's the linear in linear algebra. Okay, so that is the main theorem. There is another theorem. Well, that's not a theorem, but more of an idea. But there is another theorem which is slightly more specific. It is. Well, let me have a definition. A system of linear equations. Well, I keep writing these in the form of matrix equation, but you remember what's behind it. It's the whole bunch of them, and so this is an equation in Rn. So it means n equations with. I guess I wasn't. So in Rn, meaning that x is in Rn. How many equations is not a part of it. Okay, so we do not mention dimension b just yet. So it's called homogeneous if b is equal to 0. Okay, so it's not a big deal, but why? Because as we have not looked at b when we're solving those equations. B is just we're looking at the matrix A and do stuff with it. Whatever happens to B is just happens automatically. We never actually look at B to make decision about what to do next. It's entirely matrix A that determines it. So B could just as well be equal to 0. And what the importance of B is here. Importance or non-importance of B is here. It is S. Okay, it's not once you put the cognitive matrix in the reduced row echelon form, then the matrix the vector S is what's left of B. Okay, that you see that vector S over there. It is the shift of the whole thing from the origin. So if we, for example, if we say that the answer is a straight line, where is it? We take a vector S and put that line at the tip of that vector S. As you can see in the three-dimensional case, the story is exactly the same, even though the answer is a plane, but once again it is located at the tip of vector S. So if we don't want to deal with that extra business of having S in the way, we just put it away, out of the equation, out of consideration. So simplest equation, system of equations is AX is equal to 0. Okay. So and then there is a theory which is crucial. So a homogeneous system of linear equations with n unknowns and m equations with, now this is the crucial, you realize that the dependence of the relation between the number of equations and number of variables is crucial, right? So you might have too many equations, then you might end up with restricting so much the variables that you won't have any answer, or you have too few equations, which means that there will be infinitely many solutions. So that's what this theorem is about. So m equations, I will require that there are few or more unknowns than equations. Okay, so in general, this doesn't tell us anything. We have seen all possible outcomes when the equations we have. As you can see, I have fewer equations than variables. But it doesn't mean anything. We still could have zero answers, but not with a homogeneous system. Okay, so then has at least one non-zero solution. Well, first of all, I probably should have mentioned that a homogeneous equation or system of equations, that's really crucial, always has at least one solution. Excuse me. Zero. So once you put b equal to 0, there will be always at least one solution. So the zero solution, x equals 0, as the vector x is equal to 0. Okay, it is a solution. You plug in a vector, ax is equal to 0. If I put 0 over here, what's going to happen? Remember how we multiply matrices. So this is my matrix, and this one is the column is made of zeros only. So you can imagine what's going to happen. I'm multiplying this column of zeros multiplied by some row, which doesn't matter what that row is, will end up with zeros, right? So the 0 is always a solution. That's why the simplification is so significant that is worthwhile. Multiply 0 vector by any matrix, it will produce a 0. So, and there we have a solution. Okay, but it is considered an interesting solution exactly because it's always there. And then when is there another one that is not a 0 solution? And that's condition is very simple. You should have more equations than unknowns. Okay, so then there will be at least one non-zero solution. So can you tell me specifically what this means? What about the solution set of this equation, system of equations? If it has at least one non-zero solution. So it has 0 solution, and then that is a given. Okay, and then there's one that's non-zero solution. So what does it tell you about the solution set? Well, there are at least 2 solutions. 0 and that other vector. So, well, but we don't stop there. What's the conclusion? So there are at least 2. There are 2, at least, solutions, distinct. So what does it tell you based on the previous discussion?
There is always a solution.
Well, the 0 is always a solution.
Yeah.
But what about the solution set? What does it look like?
Oh.
Look at the possibilities. There aren't too many. We exclude what we remember that the right-hand side is 0, so I think I made that comment just a short time ago. If there are 2 distinct solutions, you can draw a line through it, and every point on that line will also be a solution. That's the thing about linearity, which we're going to discuss shortly. But at this time, we just look at the as 4-dimensional situation as we see here, and just make that conclusion, just looking at the list of all possible solutions, and look at imagine that s is equal to 0, and imagine that you have two solutions. By the way, if you're doing a homogeneous system, that column on the right, won't be any difference. You can just throw it out. Nothing is going to happen to it. When you do elementary operations, if you have a 0 there, you will be multiplying adding zeros to it, so that wouldn't produce any difference. So if we have at least 2 values, it means that the first 2 possibilities are out. Well, this is out because there's at least one solution. This one is also out because we know that there are at least 2. So we are then in one of the situations below. So if there are at least 2 solutions, it means that there are how many? Infinitely many. And in fact, you can be specific. It lists the solution set is at least one-dimensional. So once again, one-dimensional means that it has a line in it. So at the very least, it's a line. It could be bigger. It could be a plane or high dimension, but at least it's one-dimensional. So that's two numbers to be known. And you realize that to distinguish, to make a more fine distinction, one-dimensional, two-dimensional, three-dimensional, how do you know? Well, that the correspondence between n and m will be come into play along with other things. Okay, so that's a theory of what the solutions look like, and so far is always. We don't really need more than that at the time. What we want to do now is the missing part in this analysis is actually make the algorithm more specific. So how exactly do we find the row echelon form? So you did a little bit of that at home. The next homework will not be next week because of the test. So the one after, possibly there will be a bigger I think 3 by 3 at most equations. So similar to this homework, only some of them will be 3 by 3. Okay. So then well, certainly you see the issue here is you need an algorithm. Beyond that, you need to use a computer, and then you need an algorithm to explain to the computer how it is done. And the answer is well, we'll have to work it out. Okay, so any questions? No questions?
Will you talk a little bit about the test? Like
Yeah.
what exactly will be on it?
Well, I can't tell you exactly, but the problems will. I wouldn't expect them to be similar to the homework necessarily, but certainly some of them will be similar in length. Some of them will be similar in like a computation with your hands. So that will be there. But what's not in the homework is what we discussed in class, and that's the concepts. So conceptual understanding of these things. So what is the solution set? What is the vector algebra? Constant multiplication, addition of vectors, matrices as functions, like that.
So like dot product and stuff like that?
Dot products, yeah.
Okay.
Yeah.
You said you don't have the previous ones, right?
No. You can look at the linear algebra class, but it just doesn't look the same.